Hi class, this is our chapter 15 lecture about electrodes. It's going to cover indicator electrodes, it's going to cover junction potential, it's going to cover metal electrodes and ion specific electrodes. And it's also going to cover pH, so pH electrodes. Before we talk about different types of electrodes, I wanted to talk about the idea of junction potential. And I'm going to move around the screen a little bit here. I want us to think about this. An electric potential is generated by a separation of charge. So anytime we have a separation of charge, we're going to get some kind of voltage reading out of that. And anytime you mix two solutions together, and this is going to happen when we have like ion selective electrodes, but anytime you mix two solutions together, like something like a sodium chloride solution and water, you're going to get the ions to kind of mix. So at the surface here, they're mixing together. And so because of osmosis and because of a difference in concentration, the sodium ions and the chloride ions are going to start mixing with the water. And this doesn't happen all at once. In fact, one of the ions is going to mix faster than the others. And in the picture that we have here, it's the chloride ions went into the water first, and then the sodium ions kind of lagged behind. But because of the mobility of those chloride ions and them moving faster towards the water, we get a separation of charge between these two areas. And anytime we have a separation of charge, we're going to get a voltage reading there. So that's called the junction potential. And it's something that basically makes our direct potentiometry, our direct voltage readings, a little bit off from what we know they should be. So any voltage that we're going to observe is going to be what's going on in the cell plus this little bit of error, this junction potential, due to that separation of charge. And again, that separation of charge happens anytime we're mixing two solutions that are very different from each other, something like a very concentrated sodium chloride solution and water. Sodium chloride is just one example, but if it was a silver electrode, that might be something like silver chloride or other different saturated solutions. The voltage potential for good electrodes is usually really small. Okay, so it's a small potential, and you can see that it's showing the liquid-liquid junction. So this is a concentration of sodium chloride and a concentration of potassium chloride, and that would be the junction potential due to that separation of charge between them. Okay, junction potential is something that is taken into consideration when you're calibrating an electrode. And so that's something that's going to come up again when we talk about pH. Okay, now we're going to talk about different types of indicator electrodes. We're going to talk about metal electrodes first, and then ion selective electrodes. But the main difference between these is kind of what their name says. Metal electrodes are going to be made out of a piece of metal, and they develop an electric potential because there's a redox reaction happening on that metal surface. Ion selective electrodes, they develop an electric potential due to a separation of charge because one type of ion is going to be bound to a membrane, and that's going to cause a separation of charge. And that will cause an electric potential to happen. When we're talking about metal electrodes, the most common type of metal electrode is platinum. What's really nice about it is that it's extremely inert. Not a lot happens on a surface of platinum, so it's not easily oxidized. It doesn't react with things like water or almost anything else, so it keeps a nice pure surface. The con with it is that it is very expensive. All right, so even though it can be used again and again, they are hard to afford. Other electrodes that are common are gold. If you can imagine, gold's pretty expensive. Carbon is okay, except for carbon surfaces, just because graphite is really soft. Even though theoretically you can use a carbon electrode again and again, it honestly just gets like a little nicked up. Every time you touch it, little flakes come off, and so they tend to erode after a while, and they get in your solution, and it kind of messes things up. So we can use carbon. It is relatively cheap. Things like gold and platinum would be preferred if you can afford them over that, just because they are relatively hard and don't flake off and don't kind of crumble, things like that. Other metals that we can use are things like silver, copper, zinc, cadmium, and mercury. Those are good. Of course, these two are more expensive than the other ones, and the mercury is a liquid, so that kind of, causes some issues. You can't really have a solid mercury electrode. But all these metals are metals that aren't easily oxidized, and so that's how they're kind of chose. So the Goldilocks idea for electrodes, and by Goldilocks I mean kind of the sweet spot, not too hot, not too cold, is you want to find an electrode that you can afford, that is not easily oxidized and therefore keeps a nice clean surface, and you'd also like it to be a solid and to have kind of a rigid, hard shape. So actually copper is relatively soft, so sometimes we choose other electrodes over it. Mercury is a liquid, so of course that creates a few problems, but we do have some indicator electrodes that are mercury, and we'll talk about those. So not all metals are usable. Kind of the money metals are the most usable. So the reason why it's important that the metals are not oxidizable, or not easily oxidized, is because when you have a metal that's very reactive, things like magnesium and sodium, things like that, what happens is they get an oxidative coating on their surface, and so you cannot establish an equilibrium on the metal surface if it has an oxidative coating. Okay, how we would find the potential between an indicator electrode, so that's the thing that has the redox chemistry happening on the surface, and a reference electrode, is we would use the Nernst equation. Now, to be able to find the E cell for this reaction, I'm going to need to be able to look up the redox potentials for each of my half cells. And for my silver half cell, I got a reduction potential of 0.799. And for the mercury one, the Calmel reference electrode, its potential is 0.241 volts positive. Now, when you look at the relative difference between these two, because this one is higher, we know that it's going to be the cathode. And since this one is lower, it's going to be the anode. Now, when I put those into my Nernst equation, I know that E cell is going to be the potential at the cathode minus the potential at the anode. And the reason why the silver is the indicator electrode is because it is sensitive to the silver concentration. So what's happening at the cathode is it's going to detect basically a presence of silver ions. And so we need to set this up so that we're using the voltage of the redox of the silver, but we also need to take into consideration the concentration difference. One electron is being transferred, and this would be products divided by reactants, but the product is a solid here, so we don't have anything there. and this would be the concentration of silver ions. So that is what's happening at the cathode, and this dependence on the silver ion concentration is why silver electrodes act as an indicator electrode. So that's what's happening at the cathode. What's happening at the anode is just 0.241 since it is a reference electrode. So here I've just cleaned up my slide a little bit and made it a little tidier here for us. But what's happening here is this concentration of silver is going to change the potential at the cathode, and so that will change the potential that we're measuring for the cell. All right, let's do a little practice calculation where we are going to have to calculate the concentration of silver so that we can put some numbers into that Nernst equation that we just came up with. All right, I'm just going to remind us what equation we had from the slide before. It's cathode minus anode, and for us that is 799. The number of electrons. Silver is our indicator, so that's the cathode minus what's happening at the anode. And so that's the equation that we're going to use. We just actually need to find this concentration so that we can put some numbers in there. Okay, so let's read the problem. It says we have 10 milliliters of a solution that has some silver nitrate, and we titrate it with some sodium bromide there. And the first thing that I would do is I would write out a reaction. This is going to make silver bromide and sodium nitrate. Okay. Now, as the sodium bromide is made, it's going to take down the silver ions in solution. If you were to write a net ionic equation for this, it would be silver ions plus bromide ions, making silver bromide. So as we add the sodium nitrate to the silver, as we add the sodium bromide to the silver nitrate, the amount of silver ions is going to go down in solution. And we need to figure out how many of those ions are left when we've added 10 mils of 0.025 molarity bromide to 10 mils of 0.05 molarity silver ions. Okay, I cleaned up the screen a little bit, and I need to calculate how much silver is going to be left over after this reaction is done. And the easiest way I know how to do that is to kind of set up an ice table. This is also just kind of some basic stoichiometry. I need to figure out how much I started with, how much reacted, and how much was left over at the end. So what I'm going to do on the right side of the screen here is I'm going to calculate how many moles of each of my solutions I'm working with. So this is going to be for my silver nitrate solution. I'm going to use the molarity. I'm going to do a little shortcut here. I'm just going to use 1,000 milliliters instead of a liter. And then I'm going to do the same thing for the sodium bromide. I have 10 milliliters and the molarity is 0.02. Oh, got too many zeros in there. For my first one, I got 0.005 moles. And for my second one, I got 0.00025 moles. All right, so I'm going to take that information and put it over into my ice table, what I'm starting with. Okay, so that's what I'm starting with. Now, I'm looking at the difference between them. There is definitely like half as much bromide as there is silver, so that's going to be my limiting reagent. And this number doesn't really matter, but I'm just going with the flow there. Okay, so when I do the subtraction here, That's how much is left over. 0 of this is left over, and I've made that. Okay, so that number again isn't going to play into our calculations. This is the number that I am interested in. And I'm looking back at my equation up here at the top, and I realize that I should have put 1 over silver there. That was just kind of my neglect there. All right, so now I have this number. I know that there is 1 electron being transferred. That's from this right here. I now have my silver concentration, or a way to find my silver concentration, and I have that number. Now the difference between what we've calculated and the concentration is we've calculated moles down here, but we need molarity, and that's moles per liter. Like this. And divided by the number of liters, and it has to be the total liters. And my kind of total volume here is I had 10 milliliters of my silver solution, and I had 10 milliliters of my titrant, which is just sodium bromide solution. And so that is basically I have to add the 2 volumes together, and so that's 20 milliliters, and so that's 0.0200 liters. And so when I do that, I get 0.0125 molarity of silver ions. Okay, so I'm going to clean up the screen a little bit here, but this concentration is what I'm going to put up into that part of our equation there. Okay, so I'm going to do the equation. So E cell equals 0.799 minus 0.05916. And there is my concentration. Minus 0.241. Okay, so when I did that on my calculator, for this portion here, I got 0.686, and then I'm going to subtract out my 0.241, and so that I got E cell was equal to 445 volts. Okay, now I'd like to talk about ion selective electrodes. What's happening here is not a redox process, so it's not about looking at an oxidation and reduction process. What's happening is that there is a thin membrane that responds selectively to just one ion. So the good part about this is that there's no redox chemistry to take into consideration, but the kind of con is that these electrodes are good for just indicating one kind of electrode. The most common type are pH electrodes, which are selective to hydrogen ions. And so they are really good for pH, but they're not necessarily good for if you're trying to indicate silver electrodes or silver ions, something like that. So how ion selective electrodes work is there's a membrane that has a ligand in it, and that ligand binds to whatever ion it's you're trying to indicate. So here we're just going to call that the C ion, not carbon. It's just some kind of cation. So C stands for cation. Okay. And the reason why it's a cation is if you read the EDTA stuff, you would know that ligands have negative charge groups in them, and that those negative charge groups grab onto cations. Okay, I kind of want to look at this schematic that we have here. What we're doing is we are looking at the surface of the ion selective electrode where there is a ion selective membrane. So that's the part that's right on the surface. Okay, so the inside of the indicator electrode has some of the analyte that we're looking for, and it is attached to these B minuses are borate ions, and basically that's just to keep the analyte in there. And then we have the actual membrane. So this is the part that's right on the surface here. And so this is what we call an ion selective membrane, and it's ion selective because some ions are going to be attracted and make it through and other ions are not. And what's going on in here is we have some R minus. Those are actually kind of usually tetraphenyl groups that are attached to borates. So R minus, I think, oh, it even has it right here. Okay, so that's basically a tetraphenyl group attached to the borate. It's basically almost the same. It does the same thing as the borates do up here. The only difference is it binds not just to our cation, but it binds to the ligand and the cation. Right? These L's are our ligands. So that's ligand. So that's our ion binding ligand, and you can see that it's bound some of our ions in there. And then we have some free ligands, so those are the little L's. And we also, on the surface, we have some of the R groups. Those are usually not just used to bind with the ligand and the ion, but they are also used because they have a negative charge, and when the ligand and the cation bond together, they still keep their positive charge from the cation, and so we need some counter ions so that we don't have too many positive ions here. We also have negative ions to interact, and that's what we're seeing happen there. That's why the R minuses are attracted to the cations. Now, the reason why it's the reason why this is an ion selective membrane is because this ligand is only attracted to the cations. It's not attracted to any kind of counter ions. That's just any anion there. So it's not attracted to those guys. And so we say that the counter ions can't cross the membrane, or they have low solubility. So it's not that they can't cross at all. It's just that they are much less soluble than the cations, the C pluses. Now, the reason that we get a electric potential at all is because there's a difference in the concentration between the cations on one side of the membrane and the other side of the membrane. And this happens because the cations are attracted to that ion selective membrane. Now, the reason why the cations diffuse across the membrane is because there are more cations out here and less across here. So we call that a concentration gradient, and ions and compounds will always move to a place where there's basically less crowding. So the cations will move into the membrane, and because there is a separation of charge there, we're going to get an electric potential that is just sensitive to the change in concentration of those cations. And that's why we say that the potential across the outer membrane depends on the analyte solution and the concentration of those cations in the analyte solution. Now, what we're actually measuring the difference of is the difference between the inner electrode and the outer electrode, where this is pretty much a constant concentration, and this is changing due to the concentration on the outside of the membrane itself. And so to calculate the electric potential, or the electrode potential between them, we find the outer and we subtract the inner out. This is pretty much constant. So as this changes, the overall potential is going to change. Okay, so where the numbers come into play here, if we want to find the electrode potential for just say the outer, we would have to know the constant plus the change in potential due to concentration. Now this N is the number of electrons that's equal to the charge that's on the cation. If we want to know the electrode potential difference between the sides, we would have to know the difference in concentration between them, and we could calculate the potential, or if we measured the potential and we knew the inner, we could find the outer concentration, and that's really the way that these ion selective electrodes are used. Now, one of the most common ion selective electrodes that I mentioned were pH electrodes. Those are sensitive they're selective just for hydrogen ions, and that's because glass electrodes, if you treat the surface properly, as in prepare the surface properly, they can be selective to just hydrogen ions. What's nice about a glass electrode is that they're relatively inexpensive. It's not made out of gold or anything like that, and they can be really sensitive to hydrogen ions. So the way a glass electrode works is, you can see the salt bridge here, so we're going to kind of make a little line there. This part is the outer reference electrode. And then this portion here is also on the outside, but this is the solution that you're actually trying to measure. So that's our analyte solution. Okay, and then right here, this is the hydrogen ions that are in the inside, and so that's part of the electrode itself. And right here, and I'll do this in red. Right here, that is where the glass membrane is. So it's the difference between these two that we want to be sensitive to. Okay. And then this part over here is the inner reference electrode. Okay. Again, one of the things that's nice about a glass electrode is the way that they're built is it basically has the reference and the ion selective electrode in one thing, so you don't have to have two different electrodes. So I've just kind of cleaned up the slide here, and I just wanted to show you where these things are. So this inner reference electrode is basically the light gray portion here. So you can see that that extends all the way down into here. Okay. And then the hydrogen ions on the inside, they are, again, part of the solution in there. The hydrogen ions on the outside, that is the solution that you're trying to measure. So it's the solution that our indicator electrode is in, our pH electrode is in. And then this outer reference electrode, that is the dark gray portion that kind of extends all the way down through here until this tip is exposed down here at the bottom. One more thing that I wanted to point out, I cleaned this up again, but one more thing that I wanted to point out is I had said that right here, that is where the glass surface was. So this is the glass membrane that separates the inner and the outer, and that glass membrane is this blue surface around the bottom there. So that's actually exposed to the solution. The glass membrane is made out of a silicate lattice, and it has sodium ions. It has sodium ions that are bound within that structure. Now, if we look a little more closely at the glass membrane and its surfaces, you might not think about this, but say this is the glass membrane. And when you put it in water, you don't think about the surface of glass getting squishy, but that actually happens. There's this hydrated layer on the surface of the glass where it absorbs water, and because it's in contact with that water, some of the sites get occupied by hydrogen ions. A lot of them are still occupied by those sodium ions. On the inside, it's just all occupied by sodium ions because there hasn't been any water there aren't any hydrogen ions. And so we just get this really, really thin surface where some of them are hydrogen ions and some of them are sodium ions. So the way that we actually measure potential differences by monitoring actually a current carried by sodium ions. So what happens is the hydrogen ions that are in solution bind with that glass, and when that happens, the amount of current that the sodium ions have that are within the silicate in the glass, the amount of current that they are carrying changes, and we are able to measure a potential difference based on that difference in current. So the current changes due to the number of hydrogen ions bound on the surface, and that's why the glass membrane is sensitive to hydrogen ions and just hydrogen ions. It's because these O minuses, those negative sites, are selective to hydrogen ions only. Now, your book kind of has a few details about the fact that the hydrogen ions are only attracted to these oxide ions from the silicate. They don't actually make it through and like into the glass. They just bind to the surface. Now, just like any time we calibrate something, we want to have a couple calibration points. So, more is better here. When we calibrate a pH electrode, we should calibrate it with at least 2 standard buffers. And we usually do some kind of high pH buffer around 10 and some kind of low pH buffer around 4. A lot of times we actually do one in between, something like a 7. And then when we measure an unknown solution, we want it to lie within the range of those standard buffers. So when we do this type of calibration, the unknown solution that we're trying to measure should have a pH of less than 10 and more than 4. And if you do that and it's somehow out of the range, something up here, maybe you should run a calibration point, something like 12, so that your unknown is within your calibration point range. Now, thinking about the way our glass electrodes are made, our pH electrodes are made, there's some errors that are kind of inherent in the system here. So I just kind of wanted to talk about those. One of the first ones is about your standards. If the standard buffers that you're using aren't very accurate, say it just is labeled as like pH 4 instead of pH 4.00, if you only know your standards to the ones place, your pH measurement can only be accurate to the ones place. Now the next one also has to do with standards, but it's the idea of the junction potential difference between your standards and your analytes. When you use standards that are something like a pH 10, 7, and 4, and then you measure your unknown and it's something like 0.5. The ionic strength between this solution and any of these is quite different. And so what that leads to is a junction potential difference between when you're measuring this solution and when you're measuring your actual standards here. So what we want to do is we want to have standards that are close to where we know our analyte solution is. So if we ran this kind of situation, I would probably run a pH buffer somewhere around 1, which would have a closer ionic strength to my analyte solution. And so the junction potential for the electrode between measuring those two solutions would be closer than they had been before. Okay, the third one down here is junction potential drift. This basically means that the junction potential can change due to concentration. And so sometimes we, calibrate on a Tuesday, and when we come back on a Thursday, the solution has changed a little bit. So we want to make sure that we recalibrate, and we usually want to recalibrate our pH electrodes right before we use them so that we know that the calibration is most accurate to the situation that we're actually going to be measuring solutions in. Okay, now these two kind of go together. The first one is a situation in which we have very low hydrogen ion concentration. So that would be at very high pHs, and at very high pHs there are very few hydrogen ions, and the glass electrode is basically just hungry for positive ions, so it's going to respond not just to hydrogen ions but also to sodium ions that are in solution. So if your high pH solution has sodium ions, you're going to get some kind of pH reading there, and the pH that you read, so the apparent pH, is actually lower than the true pH. So effectively, you're saying that there are hydrogen ions in solution, and so you get a lower pH, but really you're detecting sodium ions in solution. Okay, and then the other one is acid error. So this is the opposite. This is when we have high concentration of hydrogen ions. At that point, the glass essentially gets saturated, and it's not responsive to hydrogen ions anymore. And so the pH, it's basically not detecting hydrogen ions anymore, which means the pH is going to be higher. It's going to read it as a more basic solution than it really is. So those are errors that happen at kind of the high and low end of hydrogen ion concentration. The next one is equilibration time. This basically it's just like our scales. It takes a little while for the glass electrode to respond and to become in equilibrium with the hydrogen ions that are in solution. So sometimes it takes up to like 30 seconds for our pH meters to stabilize their readings. And if we take a reading any sooner than that, we might not be getting the most accurate reading. Okay, the next one is the hydration of the glass membrane. We usually keep these glass membranes in an aqueous solution, and we do that so that we have that hydrated layer on the outside of the glass membrane. If that's allowed to go dry, any parts that went dry are not going to respond to hydrogen ions correctly after that. And so what happens is there's kind of like hot spots and cold spots on the surface, and it doesn't accurately respond to hydrogen ions, and so we don't get an accurate reading over the entire surface of the glass membrane. Okay, the next one on the list is temperature. It's basically saying that calibration needs to be done at the same temperature as the measurement. So we want to make sure that our calibration is as close to the actual situation that we're measuring as possible. I kind of relate it to this one up here. We want to make sure that we calibrate as close to measurements as possible. So the same temperature, about the same ionic strength. We want to make sure that we calibrate basically right before a measurement. So like I said before, we don't usually calibrate on a Tuesday and then measure on a Thursday. We calibrate on a Tuesday and we measure on a Tuesday as close together as possible so that we can ensure that the solutions have the same temperature and there isn't weird pressure changes or anything like that that can happen over a multi-day span. Okay, and the last one is just really basic. We want to make sure that our pH probes don't have anything on the surface. This sometimes happens when you have very concentrated solutions, and basically because they're close to being saturated, you get kind of a crusty surface of salt on your electrode, and that definitely changes the way that it will respond to hydrogen ions, because anywhere there's actually like physical solid in the way, it's not going to respond to hydrogen ions the way a clean surface would. Okay, the last thing that I want to talk about in this little mini lecture is the idea of selectivity. In selectivity, we are talking about the fact that in this equation that we saw before when we were talking about ion selective electrodes, we're saying that the potential, it varies due to the concentration of some kind of analyte that we're trying to indicate, that we're trying to test for. And this equation basically says that it is only responsive to the change in this concentration. But sometimes your ion selective electrode isn't exactly selective for just one thing, and there's these things called interfering ions. And so if that happens, the interfering ions basically are masked as they look like they are whatever analyte we're looking for, but they're actually different things. And so you can put on to this equation a selectivity coefficient, and the way that you would do that is instead of it just being C here, it would be C plus what we call the selectivity coefficient. Okay, and so that only happens, so instead of it just being C, it would be all this stuff. That happens when you have these interfering ions, and there's a little part, we're not really going to do any calculations here, but if you wanted to read a little bit more about selectivity coefficients, it's in 15.5. Okay, so in this mini lecture for chapter 15, we talked about junction potentials. We talked about metal electrodes. We talked about ion selective electrodes. And for ion selective electrodes, we talked about this special case of pH, which are glass electrodes. And because of the way those glass electrodes are made, we talked about kind of the errors that are inherent in there. And then we also very quickly at the end touched on selectivity.